All right, let's talk about one of the coolest, but also one of the toughest, fields in robotics today: autonomous drones. I mean, we're talking about a world where code, physics, and AI all have to come together perfectly. And figuring out how to master all that, well, that's a whole other challenge.
So if you're a student, maybe in grad school or even a developer at a company, I bet you've asked yourself this exact question. You see these amazing autonomous drones and you think, I want to build that. But man, that leap from a simple remote-controlled drone to a truly smart, autonomous machine, it feels huge, right? Like, where do you even begin?
Okay, let's just jump straight into the deep end, shall we? What you're looking at here is the architecture for PX4. It's one of the big open-source flight control systems out there. And right away, you can see it's not just one simple program. Nope, it's this whole ecosystem of different parts. You've got modules for controlling flight, for figuring out where the drone is, for handling all the sensor data, and they're all trying to communicate with each other constantly. This is the kind of complexity we're talking about. Now hold on, let's zoom in on just one tiny piece of that last diagram, the navigation filter. And boom, the complexity just explodes. This right here is the EKF2, the extended Kalman filter. Think of it like the drone's inner ear, its sense of balance. It's constantly taking in data from all these different sensors and mashing it together to figure out exactly where it is and where it's going. And here's the real kicker. The hardest part isn't learning about any single one of these boxes. It's understanding how they all work together, how they all communicate in perfect harmony. That is the gap you have to cross to get to true autonomy.
It feels like a maze, doesn't it? But what if you had a guide? Someone who's been through it 100 times, knows all the shortcuts and all the dead ends, and can just show you the way. Well, let's meet that guide.
This is Ha-Sung Wook, the head of Quad Drone Lab. And honestly, his background is pretty incredible. He's got this perfect mix of experience. On one hand, you have over 20 years as a systems engineer at LG CNS. So he's been in the trenches, building real commercial products. He knows what actually works. But on the other hand, he's been a professor, teaching this stuff at top universities. So he can break down the really complex theory. You get the best of both worlds, practical industry knowledge and deep academic understanding. That's exactly the kind of expert you want in your corner.
And this is his workshop, the Quad Drone Lab. You can see right away this is not your average classroom. It's a professional, high-tech lab. It's literally designed to help you bridge that gap we were just talking about, to take you from just knowing the concepts to actually making things fly.
So what's the secret sauce? How does the curriculum actually tackle all that complexity? Well, it's pretty simple, really. It starts from the very beginning. You break everything down to its most basic parts, the first principles, and then you build it all back up, piece by piece. That's how you get a real deep understanding, not just memorizing a bunch of facts.
You might think a course on advanced robotics would start with some crazy complex code, right? Nope. It starts with something you probably learned in high school: physics. We're talking Newton's laws of motion. The curriculum literally connects these fundamental laws directly to how a drone flies. And that's so important because it means you're not just learning how to program a drone, you're learning why it works from the absolute ground up.
Okay, so once you've got the physics down, we move on to the algorithms that actually make the drone fly. Let's take something called PID control. I know, it sounds super technical, but the core idea is actually really simple. It's all about fixing mistakes. Imagine the drone knows where it's supposed to be and it can see where it actually is. The PID controller is the brain that figures out, okay, we're a little off, so I need to spin this motor a bit faster and this one a bit slower to get back on track. That's it. The course just breaks it down so it makes perfect sense.
And here's where it all comes together. This is how that simple idea is actually used inside the PX4 software. See, it's not just one PID loop doing everything. There are layers of them, cascaded loops they're called. One loop is just focused on the drone's tilt, its attitude. Another is focused on its speed, and another is focused on its overall position. This is how you take that basic error correction idea and turn it into super stable, super precise flight. And the curriculum just walks you through it, making all those connections totally clear. But it's not all just theory, right? A big part of this is knowing how to make smart decisions as a developer. Like, should you use PX4 or ArduPilot? There's no single right answer. It totally depends on what you're trying to do. If you're building a commercial product, PX4 is probably your best bet because of its architecture and license. But if you're doing academic research, ArduPilot might be better because it has this huge library of existing tools. The course gives you the know-how to weigh the pros and cons and pick the right tool for your specific project.
And believe it or not, that's really just the starting point. Once you have that solid foundation, the curriculum builds up the whole stack. You'll get your hands dirty with the Mavling protocol, which is how the drone talks to the ground station. You'll learn to build your own apps using Mav SDK and ROS2. And then you get to the really cool stuff. We're talking about AI, like using YOLO for object detection. We're talking about VSLAM, which lets the drone navigate even without GPS, and even using special markers for landing with insane precision. The whole shebang.
Look, theory is great. It's essential. But you can't build an autonomous drone just by reading books. You need to get your hands on the hardware. So the next part is all about the tools that let you take your code and actually make it fly.
And here it is. This is the Quad Autonomous Drone Development Kit. This is your test bed. This is where you'll try out your ideas, upload your code, and see if your algorithms actually work in the real world. It's so much more than just a drone. It's your own personal lab for development.
And to pull all this together, you get this single, comprehensive textbook. What's awesome about this is that it covers everything. It doesn't matter if you're doing a quick one-day course, a two-day workshop, or the full four-day curriculum. Everything you need, all the core concepts, are right here in this one book. It's a super efficient way to get up to speed on the whole field of autonomous drone development.
But, the class ending isn't the end of your journey. Not even close. To really master this stuff, you need to keep practicing, keep learning, and have a support system. And that's something that's built right into the Quad ecosystem.
So what does that mean for you? It means you're not just left on your own after the course is over. Through the YouTube channel membership, you get access to new materials and more advanced videos as they come out. And then there's the NAVER Cafe, which is basically a community hub where you can ask questions, team up with other developers, and get help from the experts. It really is more than just a class. You're joining a community for the long haul.
Look, let's be real. Building a truly autonomous drone is not easy. It takes a solid grasp of physics, control theory, software, AI, the works. But what we've seen is that with the right guide, the right learning path, and the right people to back you up, what seems like this impossibly complex mountain becomes a clear, step-by-step climb. The future of autonomous flight is going to be built by someone. The only real question is, why shouldn't it be you?